My name is Jose Liste. I am a technical marketing engineer at Cisco. So segment routing. We know segment routing is an architecture that basically brings source routing to packet networks. And by source, we mean that the device where there is a packet injection is going to be able to impose semantics to the packet, so the packet will move accordingly through the network, according to the semantics that were imposed at the source. What that makes is that the network becomes stateless. There is no state in the middle sections of the network. All the state was imposed by the source. And what that allows us to do is to deliver a unified end-to-end network with policy awareness over the infrastructure. So, super high level of what is segment routing. Segment routing is one architecture that presents two variants of data planes. Segment routing MPLS is the instantiation of SR where the semantics that will carry the traffic across the network are MPLS labels. We call those semantic segments or segment identifiers, in short for SID. So an MPLS label is a SID. With SRv6, which is the focus of today's session, the segment is now associated with an IPv6 address. So an IPv6 prefix will now represent the segment that is going to have a meaning through the network. We begin with a very simple depiction, but it's actually very important. If you consider you have a segment routing domain between routers 1 and 2, what we're going to be doing is receiving traffic from the access, let's say from the left of router number 1, and we're going to encapsulate that inner payload, happens to be IPv4, it could be IPv6 or even Ethernet, onto an outer IPv6 header. The outer IPv6 header is the one that we're using for source routing, is the one that could potentially have a segment routing extension. We call it the segment routing header that is going to enforce waypoints through the network. At the end, we deliver the packet as it came originally on router number 2 to the right of it. So the idea is that the packet, the inner packet, will never be touched. The inner packet will never be modified. The key concept that segment routing v6 brought to the industry in 2017 is the concept of network programming. By the way, network programming is now a proposed standard at the IETF, it's RFC 8986, and it conveys the key point that an end-to-end policy is encoded as a network program, where the instructions are either in the outer IPv6 header destination address, as well as in the segment routing header extension that is part of that outer IPv6 header. What are the instructions? The instructions can be anything going from a forwarding semantic, like a fast reroute TILFA backup path. It could be a microloop avoidance path. It could be enforcement of a waypoint to achieve an internal traffic engineering policy, or even across the network when you are leaving, such as a peering policy. It's also new with SRv6. You can also have segments that have service semantics. So a SID could represent a decapsulation function for a BRF. It could represent a decapsulation function for an L2 VPN. Functions can be assigned to virtual functions, such as in NFB chains. You could have a firewall, you could have a DPI, you could have a load balancer, which now has semantics in SRv6 that can now attract traffic to it. And as you move forward, you can also find the full power being expressed on custom behaviors that one could achieve in the hardware. We have our colleagues talking about the AK based on Silicon One, where now you could actually even customize what the hardware does based on the P4 programming SDK. And you can actually even find today containers that actually run SRv6, and they can be orchestrated by Kubernetes, and they can perform functions that you want them to do in the network. if I need to express multiple waypoints into my outer IPv6 header to realize source routing, the team in 2017 proposed the segment routing extension header, or called SRh. SRh, very good news, is also a proposed standard at the IETF. It's RFC 8754, and it's nothing that completely alignment with the architecture of IPv6 25 years ago, where extension headers were possible, extension headers were proposed, and SRh is just a realization of an extension header for the purpose of source routing. Inside of the SRh, we're going to contain an ordered list of segments. And we're going to have a pointer as well that is going to tell us where are we on the network program. Are we executing the first instruction? Are we on the second instruction? Are we done with all the instructions? Those are concepts within the SRh. Now, I already mentioned a couple of standardization comments, but I will summarize in this slide. There are over 30 proposed standards related to segment routing at the IETF. Those correspond to SR-MPLS and also for SRv6. We are very pleased with the momentum and the speed that we're also moving at the IETF for SRv6. Cisco brought to IETF SRv6 in 2017, and here we have 4 key building blocks, including the core construct of SRv6. They're all proposed standards. We start with RFC 8482, which is the architecture of SR for MPLS and IPv6 data plane. We have the SRh definition, which happened in RFC 8754, also proposed standard. The core of SRv6, network programming. How do we use the SRh header and the outer IPv6 header destination address to express segments that can deliver a source routed intent? And the very last in the family are the extensions for SRv6 in our IGP, in particular for ISIS. It became a proposed standard a couple of weeks ago. We're waiting for the final numbering, but it's also proposed standard. If you look at the bottom half, what we're actually pending, and this is already well in progress in the last step to becoming proposed standards, are the extensions to BGP for signaling services, BGP link state for topology, FlexAlgo for slicing, SR policy architecture for SRTE, and OAM. So in general, the collaboration among the leading operators, the networking vendors, as well as the merchant silicon vendors is actually becoming possible. The fact that in 4.5 years, we're moving from bringing new items to the IETF for SRv6 to actually achieving standardization of the key building blocks. So it's very good news. From the adoption perspective, and these are some figures that we put together in 2020, but industry-wide, there was some number crunching that happened. We are tracking industry-wide, not only with Cisco, but among our peer networking vendors, over 100 million subscribers that run on segment routing v6 powered networks. Those networks typically began going into production in approximately in 2019, so we're looking into 2.5 years of commercial services. Industry-wide, we also are tracking around 100 deployments in different stages, architectural commitments, field trials, lab testing, or complete production, 100 more or less in total. The key early adopters, at least from the Cisco side, happen to be 5G operators in Asia.
So I think mostly service providers we are seeing the deployments. So, and if it is, which parts of the networks we are seeing usually, and use case, please.
Yeah, so what we're seeing is, well, I will expand. Beyond SP, there are some references that are not, actually there is a public reference from some companies in Japan, companies called Line, where they do run SRv6 in data centers. So yeah, the majority are SP, or the majority are 5G, where they're running SRv6 in the mid-haul and the backhaul, mostly. If you look at cases from SoftBank, Rakuten Mobile, and also cases announced by Bell Canada a few months ago. So mostly the early adopters are 5G providers. Now, what has happened over the last year and a half to the SRv6 architecture is what we called the micro-SID. And the micro-SID is a perfect extension that reuses the concept of the SRH without any change, that it uses the same principles of the network programming without any change. And in fact, what you're going to hear today is also how the micro-SIDs are a very clever leverage of CIDR and how routers perform prefix-based routing in order to move traffic over classical IPv6 routing. But now we're going to apply that principle to micro-SIDs as well. So earlier, you heard me talk about the network programming, where we can put an instruction in two places, in the outer IPv6 header destination address, or we can put instructions as well, if I need to, in an SRH. Well, it could be any type of instruction. So with micro-SID, we bring to market what we call a container SID. A container SID is a special SID that can carry multiple micro instructions. So we call them micro SIDs. In the IETF, when you review the literature, is what is called a compressed SID, and in particular, a flavor called the next compressed SID.
One of the criticisms of SRv6 when it first came out was, issues with label depth, and how does this compare to SR-MPLS? So I guess my first question to you is, as we talk about adding more functionality, where do you feel we're at with, addressing the concerns about label depth with SRv6?
Yeah, so what actually happened here is one of the key points, I'll break it into two, Kevin. One is the ability that the label depth that was created by MPLS was precluding the hardware from being able to get to the payload and, for example, perform a hashing function. With SRv6, that problem is completely gone. What we do now is we take the entropy out of the label and we put it directly into the outer IPv6 header, in particular into the flow label field. So the hashing issues and the tricks that had to happen with MPLS are gone. The second comment is more related to what you are going to be seeing here, Kevin, in the micro-SID, which is, hey, let's call a classical SID for IPv6, for SRv6, was a full-blown 128-bit instruction. So if I want to portray multiple instructions or multiple waypoints, I'm now being forced to push multiple of these full-blown IPv6 addresses into the SRH. So now my SRH goes larger. With micro-SID, we tackled that head-on, Kevin. You're going to see how we can express multiple waypoints, and we actually maintain the simplicity of a smaller number of IPv6 addresses that I need into my SRH, or even removing the need of the SRH for most of the cases. And I can still portray the different semantics of my waypoints that I want to realize. So micro-SID will actually be one answer to that, to the good question you asked. So we'll cover that here.
Got it. So I think that partly answers the second part of my question, which was going to be how do you see, if we have addressed, concerns with label depth, how do you see additional functionality affecting issues with label depth and scalability in the future? Yeah.
So in fact, we strongly believe that with the micro-SID approach, you are going to see that the most common cases that we see today requiring less than 10 labels will be handled without SRH directly in one IP encapsulation. And if an SRH is needed, you will find SRHs that only have one IPv6 address inside of the SRH. You move fast forward to Cisco, and Mauricio and the team will be talking about the Cisco AK. We are developing ASICs that today will be able to deliver 20 micro-SIDs at line rate, which is going to be way over more than we predict will be 10 or so segments. So we are moving very quickly, and the hardware is moving to support the capabilities that are needed to succeed.
One of the big draws to SR-MPLS was the potential for interoperability and interconnection with a PCE that can talk to, basically any platform that will do PSEP and SRMPLS. What is the, do you know the current state of interop between this micro SID approach that you've implemented, and what other options are available? Is there any other option for micro SIDs on any other platform? Because I've never worked on a service provider network that only has one vendor in it.
There is no point that anything related to SRv6 or SR in general would have succeeded if it was only single vendor. What happens, and it has already happened, there are already multiple interoperability proofs and public and private events where we have taken SRv6 in general for an interop run, Nick. And that was actually most of them running with the classic 128-bit SID. In micro SID, Cisco has already proven interop with other vendors. In particular, you can find at segmentrouting.net some of those references, in particular with Arcus. We have customers who have run private interops with other companies that they happen to use in their networks. And there are still multiple private interops specific to micro SID, Nick, that are going to be coming up. Overall, we expect that 2022 will be a very key year where we're going to see more momentum that is going to translate into more proofs that of the micro SID architecture across multiple vendors. It will not be a single vendor option.
I'm wondering, one of the criticisms of SRv6 has been around just, header overhead. Because you're using, a lot of IPv6 addresses, right, as SID. So is that what micro SID is supposed to address?
So we are looking at the head-on at the MTU efficiency and how can I express more waypoints without overloading the overhead that I need to impose into the packs.
From that aspect, similar to SRMPLS binding SID?
No, it's orthogonal. Actually here, the binding SID construct, Orhan, applies to both SRMPLS and SRv6. So you have the ability to have an SR policy in either flavor of the data plane where you can actually provide opacity to a particular path where you want to explode it. This actually goes orthogonally to that, Orhan, where we can express more without having to impose full-blown 128-bit segments. Is orthogonal to the binding SID. And the concept is based on what we call a micro SID container. A micro SID container is basically a full-blown 128-bit SRv6 SID. The container will carry a micro SID block, which is really going to be the leading part of the container. It's actually an IPv6 prefix that is available to the provider. We will talk more about what are those IPv6 prefixes in real practice. But imagine you have your container, you have your block, which identifies a block of micro SIDs, and then you have the micro SIDs. The micro SIDs, each in blue here, will represent each one of them a semantics to achieve a particular goal. They are a type of a compressed SID. And as you can see, you could have multiple. And then at the very end, you will have a special reserved micro SID, which is going to call the end of container. When we do micro SID, the network programming now takes us to the micro program. And the micro program will be read from left to right, where I jump from my active micro SID to my next micro SID until I get to the last micro SID. We'll show you that in the sequences coming up. The meaning of the micro SID is exactly the same I told you when we had full-blown SIDs. All the different semantics, topology, service, functions, etc. In real life, when you look at an example of a micro of a carrier container, the first point to talk about is the block. The block can be allocated from the private IPv6 space, so FC/8 as a non-routable. Hence secure, or it can also be a public prefix that has been assigned to the operator. We recommend blocks that are /32 prefixes. They can also be /16 or /48. Pictorially, I think the last bullet is the important one. You can imagine now that in your network you could have blocks For SRv6, you can have in blue a /32 block where you represent your minimum cost slice, which is basically the shortest path based on the minimum minimizing the IGP metric. Or you could have a red slice with the red /32 prefix, which represents your minimum delay slice in the network. This time minimizing for the link delay measure on every link in the topology. Now, when you move from the block, then you realize you now have your microseeds. The microseeds by default are also of a particular size. They are 16 bits. So for nibbles, W, X, Y, Z, they can also be of different size. They can be 32 bits if you need to go ultra scale and you need to have over 4 million microseeds that you want to address. But when you use four nibbles, 16 bits, you can carry, when you do the math, 6 microseeds inside of the carrier. So 32 for the block, and then 6 for 6 microseeds. That would be for a total of 128 bits. And when you read the program, intuitively, you're going to say, with this address that we have in the picture, we're going to say we're going to move in my block that minimizes the IGP metric, and then I'm going to follow the shortest path to the parent that owns the microseed 111, and then I'm going to move to the parent that owns the microseed 222, and so on, until I get to the node 666. But what happens if I need to have more waypoints, and I would like to have, let's say, 10, 11, 12, 16 microseeds, 12 microseeds. In that case, what we do, as I mentioned before, the outer destination address will carry the first 6 microseeds expressed with the prefix of the container, followed by all the microseeds. And then in the SRH, in the outer IPv6 header, I could have another carrier, another container. In this case, the second container inside of the SRH will include the subsequent 6 microseeds. What that is going to produce is going to give you the ability to express 12 microseeds with very minimal overhead, one outer destination address, and one SRH with only one IPv6 prefix for only 24 bytes of MTU overhead. And if you look at the curve, when I look at the blue line that represents the overhead of microseed, my overhead remains pretty constant when I'm moving into 6 or from 6 to 7 to 12, and we compare that to, for example, doing MPLS with a B6 data plane, where I have to, for example, hypothetically run 12 labels. So the efficiency of the MTU overhead is deterministically and mathematically lower with microseeds. Now, back to my hypothetical network, as I mentioned, 2 blocks, one for delay and one for cost. I go into a device number 2. This particular device will have now a participation into both blocks. He's going to have an instruction that means come to 2, minimizing the IGP cost, and that will be my /48 in blue. And I'm going to have similarly a /48 that means come to 2, minimizing the delay. Those 2 /48 prefixes, because they're really prefixes, they will be advertised in ISIS, and a router on the opposite side, like router number 1, in their forwarding table, they're going to program basically a fib entry on how to get to 2 for the prefix in blue /48, for example, if the IGP computed via interface 0, and another prefix in red /48 via interface 1. They represent different paths in the network. And this is where we're going to be moving into very important constructs. Everybody in the network is going to be doing prefix-based routing and forwarding. Now, not only ISIS, but now BGP. If I'm running services between router number 2 and router number 1, I'm going to be advertising VPN prefixes, and those VPN prefixes, in addition to the normal, the prefix, the RD, the RT, they will also include the SID that that particular VPN prefix and the intent in the transport requires. Imagine, for example, that I want to advertise this prefix 10.2.0/24 in VPN number 9 over the block that minimizes the cost in blue. So now the SID that will be advertised by BGP, it will include the carrier, including the segment of how to get to 2 in the minimum cost block, and now another instruction, in this case F009, which is an instruction that will tell router number 2 to do a VPN 9 decap. If you remember, in MPLS, you had an MPLS label signaling how to do decap. In this case, you have an SRv6 microSID instruction, F009. And if you wanted to advertise a prefix in the VPN where you want that prefix to be carried, minimizing the delay towards the BGP next hop, then BGP will advertise a different SID. And instead of advertising the instruction of going to 2 via the minimum cost, in blue now is in red, minimizing the delay going to 2. My VPN decap function is the same. Now, to see this in action, I decided to bring one of the use cases that are very well common and documented by the web operators, specifically when they're trying to achieve decisions like egress peering engineering, which is controlling how to get traffic out of their network. In this case, the idea is to be able to run SRv6 directly at the host. The hosts are going to be controlled by their, for example, their SDN controller. And the idea is to realize a path where I can move within my network through specific waypoints. I want to go via 3, via 4, via 5, via 2. And then once I get to 2, I want to go exclusively out via peer Y, not via peer X, which is what BGP may have been doing in my BGP next hop criteria. So that's really the end goal. The idea here now with microSIDs is that a controller can program directly the host. It can program directly a container. It can program directly an application to tell it, for this application, I want you to impose this outer destination address. And the outer destination address in blue is going to do everything I said in English. We go to 3. And then we go to 4, and then we go to 5, and then we go to 2, and then we leave via peer Y via the instruction F002.
What if you want to do not like strict hop like this, but loose hop? You could do it as well, right?
Yeah, in fact, what's going to happen, Orhan, is that going to 3, I'm going to be traversing many routers here in gray. So I'm going to 3, following shortest path to 3. And then I follow shortest path from 3 to 4, traversing many, many routers. So,
and you don't have to specify them, yeah.
No. In fact, I don't have to specify them, Orhan. And in fact, these routers are pure transit. They don't even need to be SRv6 aware. Only the routers which are in the waypoint, they need to know about how to handle the SRv6 overhead, but not the transit routers. This is the key reason why SRv6 is picking up so quickly, because the seamless deployment characteristics are very unique. Not like in MPLS, where I had to run MPLS everywhere. I could have transit nodes that are completely purely IP. It's a big fact. And here is the answer to your question, Orhan. When you look at what is happening at this first gray point, he's just going to be doing a longest match lookup and following his routing entry and his forwarding entry for the longest match. In this case, the longest match is the /48 that was advertised by node 3. That's all what he's doing. He does not care about the other elements of the other microSIDs that are in the container. He doesn't know about them. He only knows about the longest match based on the /48 that was advertised by router number 3. This is pure classical IPv6 routing. This is pure prefix-based forwarding with longest match lookups. Now, 3 is different. 3 happens to be in the waypoint, so he's going to recognize that his :003/48 is in the destination address. Is going to match his own programming entry, and he's going to apply what we call the next behavior. With the next behavior, what he's going to do is he's going to promote the next microSID to become the active microSID. So as the packet leaves 3, the DA will be modified. And instead of having 3 as the active segment, the active microSID will now be 004. So what we have done is we have shifted the micro program. We have shifted the program to the left. We activated a new micro instruction. And when we do that, you can see at the end, we have appended the well-known end of carrier microSID. So I always keep the structure of the outer DA. This is what happened on 3. And now you know what's going to happen in the next 5 clicks. The next router between 3 and 4, he only follows now the /48 that was advertised by router number 4. That is his longest match lookup on how to get to 4 following the shortest path. 4 is special. 4 will behave like 3, and 4 will do the next shift. So now 5 is the active microSID in the topology, in the carrier. 5 will be transit. 5 will do the shift. Router between 5 and 2 will also be transit. Now, router number 2, this is important. Router number 2 is attracting traffic, and he's also doing service termination. What he's going to do is he's going to be able to do in one lookup, he's going to be able to parse 2 instructions. The instructions that are come to me and the instruction F002. So here I have a /64 that I'm going to be applying in order to realize my end goal of EPE behavior. We have seen tremendous momentum in SRv6 over the last 2.5 years. Production deployments are in place. We have broad adoption. When you look at SRv6, we are having more vendors claiming official support. We were the leaders, but other companies are now jumping on board. So this is good for the industry. The SRv6 is moving at a very good pace. We're very happy with the fact that the building blocks are being standardized. And we think, as I said a moment ago, that microSIDs in 2022 will play a big role in our competitors as well as in our customers' offering.
So where's the state of interop for SRv6 these days?
Yeah, so I actually mentioned this. So we have done public interop with the classic SID SRv6, the 128. So we typically go a couple of once a year at least to do some interop at public events. They're called EANTC. So we have done interop with Nokia, Juniper, and Huawei. You can check the results from 2021. And there are more interop events that are happening in private as well, Kevin. But interop readouts are happening and they're public, and you can check them out